Welcome back to the video course on fluid mechanics. The last lecture we were discussing about the dimensional analysis, similarity and similitude and model studies. So, we have seen what are the importance of dimensional analysis, and we have discussed two important methodologies as far as dimensional analysis is concerned. One is Rayleigh's method and the second one is Buckingham's pi theorems. So, we have seen how we are doing the dimension analysis with respect to this Buckingham pi theorem, and then what are the importance of each pi term and how we are getting the dimensional terms with respect to the pi terms described in the Buckingham pi theorem. So, now before going further, we will just see the important points to be remembered while doing this dimensional analysis using Buckingham pi theorem, which is the one of the most commonly used methodology. So, the important points to be remembered in dimensional analysis while using Buckingham pi theorem are: first one is the selection of repeating variables. So, number of variables will be repeating with respect to each pi term, so that we should be how we select. Second one is determination of fundamental dimensions. So, we have seen that either MLT, mass, length, time, or FLT, force, length, time, these are the fundamental dimensions we use. So, with respect to this, we have to decide which the fundamental dimensions we use, and then next one is manipulation of pi terms. So, we have seen how we are forming each pi term. So, in the dimension analysis, we may have to manipulate these pi terms, and then uniqueness of pi terms. So, with respect to the analysis, whether the pi terms which we are using is unique in nature, or the uniqueness we have to test, and then determination of pi terms by inspection. So, these are the important points to be remembered in dimension analysis using the Buckingham pi theorem. So, as far as the first point, selection of repeating variable is concerned, so this is one of the most important step in dimension analysis, since we will be identifying which are the terms which will be repeating, and then how we will be utilizing it. So, here we are finding out the number of repeating variables, that is number of fundamental dimensions involved. So, this must contain all the fundamental dimensions. So, in the analysis, all fundamental dimensions should be covered. There is no hard and fast rule as far as the way which we select the repeating variables which include the fundamental dimensions. So, generally it can be mass, length and time, or force, length and time. So, either we can use MLT system or FLT system. So, this selection of repeating variable is one of the most important step as far as dimension analysis using the Buckingham pi theorem. So, next one, we have to select from all types of parameters, whether in the dimension analysis we will be dealing with the geometric or material property and external effects. So, with respect to all this, we have to select all the important parameters. So, as far as geometric properties are concerned, we have to define the shape and the size of the body, length, angles, etc. So, here when we do the modeling, so we have to see that whether we are going to construct, say for example, if we are considering the flow over a cylinder, with respect to this, if we are doing a model. So, we have to see what will be the dimension which we are going to model in this, and then the size of the cylinder and all other parameters we have to define. So, geometric properties define the shape and the size of the body, that is length, angles, etc. And the second one is the material property. So, this material property defines the type of response of body under the action of the forces. So, like which say in a fluid mechanics we will be dealing with various kinds of fluids. So, the density of the fluid and then the viscosity of the fluid. So, all these things related to material property we have to select and consider appropriately in the dimensional analysis with respect to the methodology we use. And then external effects are the forces due to the pressure, velocity, gravity, etc. So, when we do the dimension analysis, so we have to see that how the forces are acting, or how the pressure is varying, or how the velocity and gravity are affecting the particular the model or a particular study which we do. So these are some of the, when we select the different types of parameters, we have to take care of the geometric property, material property, and the external effects. And then next point is the dimensional multiplication of the variables should not be non-dimensional. So when we in the dimensional analysis using Buckingham pi theorem, we have seen how we are doing the various groups will be multiplied. So we have to see that we have to check the dimensions of variables such that the dimension of the multiplication of the repeating terms does not get nullified. So this is another important point. The dimensional multiplication of the variable should not be non-dimensionals. And then the next point is in fluids, the density, velocity, and the term d, which represents the geometry, are used. So the rho represents the material property, d represents the geometry, and v represents the external effects. So these parameters we have to take care in the case of say dimensional analysis using the Buckingham pi theorem. And then the other important point is we have to decide the fundamental dimensions which we will be using. So the dimensions in the Buckingham pi theorem or this methodology, dimension should be able to describe all the variables involved, either m, l, t, mass, length, time, or FLT, force, length, time systems can be used. So depending upon the case, whether we can use MLT or FLT systems, and if any problem having the fundamental dimensions as f and l only, then their f should be represented as f is equal to ml t to the power minus 2, that means mass into acceleration, force is equal to mass into acceleration. So this we have to represent the force in this form, f is equal to ml t to the power minus 2, so as to introduce the time components there. So these are some of the important factors when we decide the fundamental dimensions, either MLT or FLT systems. And the next point is the manipulation of pi terms. So when we discuss the Buckingham pi theorem, and when earlier we have seen how to solve a particular problem with using Buckingham pi theorem. So we have seen that some of the pi terms we can manipulate to get appropriate form of dimensional form. So with respect to this, the manipulation of pi terms possible in the Buckingham pi method. So any pi term, some of the important points as far as manipulation of pi terms are, any pi term can be represented as a function of other pi terms. So we have seen, we have represented the pi terms with respect to as a function of pi e can be, here we have already seen pi as pi 1, pi 2, pi 3, etc. So out of this number of pi terms, we can represent each with respect to other pi terms. So any pi term can be represented as a function of other pi terms, and the pi terms can be expressed in combinations of more than one pi terms. So this is also possible. Then third point is pi terms can be multiplied by constants. So we can represent each pi term by multiplying by another constant term. And then next point, pi terms can be given any exponent suitably. So we can, when we represent the pi terms here, you can see that we can put with respect to a, b, c, or we can multiply with respect to by using a constant, or pi terms can be given exponent suitably, and as a function of pi term, other pi terms can be used as reciprocals also. So while doing the dimensional analysis using Buckingham pi theorem, so the pi terms can be manipulated different ways, like we can represent one pi term with respect to other pi terms, or we can multiply with respect to constant, or reciprocals can be used, or we can suitably give the exponents such that we get appropriate form of the dimensional dimensionless form, or the appropriate equations can be formed. So, this very important as far as Buckingham pi theorem is concerned. Here we can manipulate the pi terms at different ways, so that we will get suitable forms. Next point is the uniqueness of pi terms. So, we have seen in the Buckingham pi theorem analysis. So, each pi term depends upon the selection of the repeating variables. So, we have seen there are certain repeating variables. So, in this the pi terms depends upon the selection of which are the repeating variables. So, for the same variables we can get different pi terms if the repeating variables are different in two cases. So, for example, if two cases the repeating variables are different, then the same variable can get different pi terms. So, say for example, here you can see in problem independent variables are say rho the density, v is the velocity, d is the geometric like diameter, length or breadth, and mu is the viscosity. So, now choosing the repeating variables we can use as rho Vd or rho and rho Vd gives different pi terms. So, here if we choose say rho Vd, we can choose in different ways, so that it will give different pi terms. So, as we can see there is not a unique set of pi terms which arise from dimensional analysis. So, in the dimensional analysis we can see that there is no unique set of pi terms. So, however, the required number of pi terms is fixed. So, in the analysis which we have seen the basic steps we have seen earlier, the number of pi terms is fixed. So, there is not a unique set of pi terms which is coming from the dimensional analysis. So, once the correct set is determined, all other possible sets can be developed by a combination of products of powers of the original set. So, what we do say once this different pi terms are defined and required number of pi terms are fixed. So, what we can do, the correct set which we require we can determine by a combinations of the products of the powers of original set. So, this is the as far as the uniqueness of the pi terms. So, this uniqueness also we should meet while doing the dimensional analysis using Buckingham pi theorem. So, next one is the determination of pi terms by inspection. So, while say doing the dimensional analysis by using the Buckingham pi theorem, we can do some inspection, or we can check and we can determine the pi terms which way it is coming. So, here it is quicker method of determination of pi terms by inspection. It involves trial and error strategy. It is based on the principle that the pi terms are dimensionless, and then by inspecting the individual dimension of the parameters, pi terms can be formed, and pi terms can be combined to form relationship in between them. So, once say we decide the repeating variables, the fundamental dimensions, and then say while inspecting the particular while checking the particular problem, so we can say through inspection say or through trial and error we can decide the pi terms, say the how the pi terms are formed, or which way we can combine each pi term. So, these are some of the important points which we should take care while doing the dimension analysis using the Buckingham pi theorem. So, even though we sometimes we use Rayleigh's method, but as we have discussed earlier, Rayleigh's method has got some limitations. If the number of parameters or variables increases, then Rayleigh's method is not suitable. So, we have to go for the Buckingham pi theorem, and then we have seen how we are doing dimensional analysis using the Buckingham pi theorem. So, different possibilities are there we can manipulate the pi terms, and we have to only check the uniqueness with respect to the pi terms, and then we have to see that the appropriate for the groups are formed, and we can use the Buckingham pi theorem in the for the dimensional analysis. So now these two important methodologies are used in the dimensional analysis. Now further we will see how this in the dimensional there are number of dimensionless numbers or groups in fluid mechanics, which is formed by various aspects, various theories. So now we will discuss the common dimensionless groups in fluid mechanics. So here in this slide you can see here we will discuss the various dimensionless group. First one is the Reynolds number. So we have already seen the importance of Reynolds number in fluid mechanics. By determining Reynolds number, we can see that the flow is whether laminar or turbulent, or say we have the various fluid flow parameters, various we can classify the flow according to the Reynolds number. So Reynolds number is one of the most important dimensionless group in fluid mechanics. So this Reynolds number is the ratio of inertia force to viscous force. So there were two important forces in most of the fluid flow. One is inertia force and second one is viscous force. So the Reynolds number gives a ratio of inertia force to viscous force, and Reynolds number is expressed as R is equal to rho V L by mu. So where rho is the fluid density, V is the velocity, L is the characteristic length, depending upon the case, whether it is length or it is for example pipe flow, L is representing as D, the diameter of the pipe. So and for open channel flow it is the length dimension. So rho VL, mu is the coefficient of dynamic viscosity. So the dimensionless group Reynolds number is defined as ratio of the inertia force to viscous force, and expressed as rho VL by mu. Second number is Prandtl number. Prandtl number is the ratio of inertia force to gravity force. So especially in the case of open channel flow, we can see that the fluid flow is governed by the gravity force. So this, say for example, if we consider a flow through a channel like this, so here you can see that with the inertial force, another important aspect is the gravity force. So here the Prandtl number is another important dimensionless group, especially used in open channel flow. So here it is the ratio of inertia force to gravity force, and it is expressed as the Prandtl number Fr is equal to V by root GL, where L is the characteristic length. It can be depth or it can be say various other parameter depending upon which way we are dealing the problem. So it is the Prandtl number Fr is equal to V by root GL, or L can be, in the case of open channel flow, it can be depth of flow. So the dimensional number is second one is Prandtl number. This is also very important wherever the flow is governed by especially gravitational effects are there. So that this, based upon this dimensional number, dimensionless number will be say making models in fluid mechanics. Third number is called Euler number. So Euler number, it is the ratio of pressure force to inertial force. Euler number is defined as the ratio of pressure force to inertial force, and it is EU is equal to P by rho V square, where P is the pressure, rho is the mass density, V is the velocity. So wherever say we deal with the fluid flow where pressure is, say we have to consider effectively, there we define this dimensionless number, Euler number. Next dimensionless important dimensionless number is called a Mach number. So, Mach number is the ratio of inertial force to the compressibility force. So, here this is defined as m is equal to v by c, where v is the velocity of flow, c is the speed of sound. So, here this number dimensionless number is used wherever the compressibility effect is very important, especially in aerodynamics we use Mach number. So, where c is the speed of sound, which is say with respect to this speed of sound only, we define the Mach number. And then another important number is called a dimensionless number is called a Weber number. So, Weber number is the ratio of inertia force to the surface tension force. So, many fluid mechanics problem surface tension is very important. So, here we can use this Weber number, the dimensional number Weber number. So, this Weber number is defined as rho v square L by sigma, where rho is the density of the fluid, v is the velocity, L is a characteristic length, and sigma is the surface tension force. So, here Weber number is defined as rho v square L by sigma. Another important dimensional number is Cauchy number. Cauchy number is the square of Mach number. We have already seen the Mach number. So, Cauchy number is defined as the square of Mach number, and it is defined as Ca is equal to rho v square by Ev, where v is the velocity, rho is the density, and Ev is the bulk modulus. So, here also depend the wherever the cases the compressibility effect is much more important, the Cauchy, the dimensional number Cauchy number is utilized. Some other numbers like dimensional number, like another important number is called a Strouhal number. So, Strouhal number is the ratio of local inertia force to convective inertia force. So, wherever the convective forces are important, so here we use this Strouhal number. So, Strouhal number St is equal to omega L by V, where omega is the frequency of oscillation, L is a characteristic length, and V is the velocity. So, the Strouhal number is the ratio of local inertia force to convective inertia force. Another important number is Prandtl number. So, Prandtl number is, it approximates the ratio of momentum diffusivity and thermal diffusivity, wherever the thermal effect also considered in fluid mechanics. Here we use the Prandtl number. So, Prandtl number is defined as PR is equal to nu by alpha, where nu is the kinematic viscosity and alpha is the thermal diffusivity. So, this number is very important wherever the thermal effects also considered in fluid mechanics. This is the Prandtl number, PR is equal to V by alpha. And then another important number is called a Fourier number, dimensions number. Fourier number is the ratio of kinematic viscosity or diffusivity to advection. So, here the Fourier number is defined as nu by UL, where nu is the kinematic viscosity, U is the velocity, and L is the characteristic length which we consider. So, Fourier number is defined as Fo is equal to nu by UL, and then another important number is called a Peclet number. This Peclet number say is dealing with the wherever the advection is also important. So, Peclet number is the ratio of advection to diffusion effect. So, this is actually the product of Reynolds and Prandtl number. So, the Peclet number is defined here, P is equal to UL by alpha, where U is the velocity, L is the characteristic length, and alpha is the coefficient of diffusion. So, this Peclet number is very important, especially when we do numerical modeling. So, wherever say especially transport equation, so transport of say various particle or contaminant or concentration. So, with respect to this, when we do numerical modeling, we will be checking the Peclet number, so that we can see that the numerical modeling which we develop will be stable with respect to the various other parameters. So, this is called a Peclet number. And another important dimensionless number is called a Richardson number. So, wherever the buoyancy effect is very important, this number is used. So, Richardson number is the ratio of buoyancy gradient to velocity gradient, and this is expressed as Ri is equal to G by rho del P by del Z divided by del U by del Z all square. So, this is the Richardson number, and another important number is called Rossby number. Rossby number is wherever the rotational flow is. When we deal with rotational flow, we will be using this dimensionless number Rossby number. So, here this is the ratio of velocity to rotational velocity. So, this is expressed as Rho is equal to U by omega L, where U is the velocity, omega is the angular velocity, and L is the characteristic length which we consider. And two more important numbers which we generally use in fluid mechanics is an Ekman number. So, here again wherever the rotational effects are considered. So, here Ekman number gives the effect of viscous terms to rotational terms, and it is defined as Ek is equal to nu by omega L square, where nu is the kinematic viscosity, omega is the angular velocity, and L is the characteristic length. And say wherever this rotational flows are considered, there the reciprocal of Ekman number is defined as Taylor number. It is omega L square by nu. It is Ti is equal to omega L square by nu. So, this is also used wherever we deal with the rotational flows. So, there are a few more numbers which are using depending upon whether say various other branches of fluid mechanics. So, but these are the few numbers like Reynolds number, the Fruit number, Weber number, then Cauchy number, then Prandtl number, then Fourier number, Peclet number, and Richardson number, Rossby number, Ekman number, Taylor number. So, these are some of the important dimensionless numbers which we use in fluid mechanics, but a few more dimensionless numbers are there. So, now let us see with respect to these dimensional numbers where are the applications. So, we have seen each dimensionless groups of dimensionless numbers, it is a ratio of say some force terms to other terms, like that it is a ratio between two terms. So, depending upon the problem, so we have to choose a particular set of dimensionless numbers, so that we can say further critically analyze that particular problem with respect to these dimensionless numbers. So, let us here we will discuss the application. So, the corresponding dimension. So, here in this table the dimensionless number is terms are written and its corresponding application is written. So, first one is the Reynolds number. So, Reynolds number is, as we have seen, this gives this number gives a classification with respect to laminar and turbulent flow, and it is used in all fluid mechanics problems, but especially when we deal with the closed conduit flows like pipe flow, we directly define the Reynolds number, and then with respect to that we classify, and also open channel flow also we can utilize the Reynolds number. And the second one is the Froude number. So, Froude number, the application is so wherever the flow with free surface is involved. So, like we have seen the open channel flow. So, open channel flow wherever the free surface is important, there we use the Froude number. And the third number is the Euler number. So, Euler number we have seen it is for wherever the pressure flow is considered. So, in the case of pressurized flow, Euler number is important, and there we will be considering Euler number. And Mach number is considered especially aerodynamics flows. Wherever compressible flows are important, there we consider the Mach number. And Weber number is concerned, especially whenever surface tension is important for the flows for the fluid mechanics problems, wherever surface tension is important, we consider the Weber number. And then Cauchy number also, wherever the compressible flow is considered, we consider the Cauchy number. And Strouhal number, wherever the unsteady effect is, we say we have to critically analyze, then in that case we use the Strouhal number for unsteady flow analysis. And then a few other dimensionless terms or numbers which we have already discussed, say for example Fourier number, wherever we deal with the transport of fluid flow. So, there in that case say the Fourier number is important, and we use the Fourier number. And then Peclet number, as I mentioned, this shows the with respect to the advection and diffusion process. So, especially advection process is important, there we use the Peclet number. So, they also used in numerical analysis, numerical modeling, like using finite difference, finite element method, we will checking the Peclet number to see that the numerical method is stable. So, then other numbers like Richardson number we use for wherever the fluid is say stratified flow, like say due to temperature effects. Say for example, if you consider a say fluid flow process in a lake, you can see that here we have got a lake. So, with respect to the temperature, there can be stratification. So, for stratified flow is concerned, this Richardson number is very important. So, one will be say cold water, say, or with respect to this is T1, T2, the temperature variation is there. So, more cold or less cold, like that stratification is there. So, in that case the Richardson number is very important. And then the Rossby number, the application is geophysical flows, like say when we consider the flow in the sea or estuary flow, or like wherever the geophysical say like with respect to the Earth's rotation is important. So, that kind of flow, geophysical flow is concerned, Rossby number is important. And Ekman number, we can see that wherever Ekman layer formation takes place, and then rotating flows, this is also important for say the coastal flow analysis, or Ekman number is also used. So, wherever rotating flow is important, we use the Ekman number, and Taylor number also wherever rotating flow is considered we use, and Prandtl number wherever the efficiency of fluid transport with respect to momentum relative to heat is considered, there we use the Prandtl number. So, these are some of the important dimensionless groups of dimensionless numbers or terms which we use in fluid mechanics, and then its applications, important applications here we have discussed. So, that is about this dimensionless group of numbers. Further we will be, when we go to the model scales and model studies, again further we will be utilizing some of these dimensionless numbers, and then we will be finding out the scale ratio or the model scale with respect to these dimensionless numbers. So, before going to the model scales and scale ratios, we will discuss about the similarity or say similitude which we utilize in dimensional analysis or in fluid mechanics. So, as I mentioned, most of the time in say many analysis in fluid mechanics, we develop models in the laboratory. So, there is a prototype or the actual field problem is there. So, with respect to that field problem, we will be developing scaled models in the laboratory. So, while doing this say modeling in laboratory, especially physical modeling, we have to see that what kind of similarities are possible with respect to the real field problem and the model which we develop in the laboratory. So, we can see that as far as the real field problem is concerned, the dimensions, length, breadth, width, or the depth of flow, all these parameters we have to consider, and then we have to deal with the velocity, then discharge, then acceleration or time component, and then also we have to deal with the various forces coming on that particular problem, say like inertial forces, viscous forces, gravity forces, or surface tension forces, or pressure, etc. So, all these parameters, so when we develop a physical model of this real problem in the field, so we have to see that what kinds of similarities are possible. Most of the time exact kinds of modeling will be difficult, so we may be developing the physical model with respect to certain say similarities and other similarities. So, we may be neglecting. So, while doing this modeling exercise, we have to understand what are the important parameters, and then we have to analyze these parameters, and we have to consider when we develop the model with respect to the real physical problem or with respect to the prototype, we have to see which are the dominating parameters, and that parameters we have to consider in the scaled model which we develop in the laboratory. So, here you can see in this slide, say this is a model of the an estuary problem. So, wherever say a river is joining the sea, so here various aspects you can see that we may not be, so the scale is concerned, the length scale, the width scale or depth scale, we may not be able to follow the same way. So, we have to scale appropriately, and also we have to see that the velocity of flow coming from the river to the sea, how it is behaving, and then we have to consider various important forces. So, the essence of modeling here is to create a flow similar to that in prototype. So, that is very important. So, our aim is, so we are investing a lot of money, time, and we are doing research to develop a particular model corresponding to a prototype or corresponding to a field problem. So, when we do this, our aim is, so if we can say how much possible, or we are always trying to create very similar kind of with respect to prototype up to the possible level we will be trying. So, the similitude or the similarity is very important in modeling, especially physical modeling in fluid mechanics. So, we will be discussing various aspects of this similitude here. So, the concept used in testing the engineering model. So, as I mentioned, so when we develop the model, this similitude or similarity principle is used very much, and the similarity of behavior for different systems with equal similarity parameters we have to consider while modeling, and then the relation between the model and prototype. So, we are representing the prototype with respect to the model. So, this which are the similarities possible or similitude is possible. So, with respect to that only we will be getting various relationship, and then this similitude or the similarity principles helps in calibrating the model from the prototype. So, with respect to this, say most of the time we have to calibrate. So, once we develop a model, so actually in the field problem there will be certain observed values. So, with respect to these observed values, so we will be trying to say calibrate. So, say by varying various parameters, so that here the calibration process, through the calibration process the model with respect to the prototype, we will be developing various relationship. So, this calibration is this similitude which we consider, what kind of similitude or similarity we consider, this helps in calibrating the model from the prototype. So, while doing this kinds of physical modeling, generally 3 important similitude or similarity principles are used in fluid mechanics. These are, first one is the geometric similitude, second one is the kinematic similitude, and third one is the dynamic similitude. So, here say the geometric similitude means, say it is the similarity between the various length parameters of the model and prototype. So, the real field problem which we consider the with respect to the length or with respect to the breadth or the depth or various dimensions of the real field problem. So, how we model or how we do the similarity, this is the geometry. Geometry means length, breadth, and depth. So, with respect to these parameters, how the similarity is adopted or the similitude is adopted. So, that is we deal with the geometric similitude, and second one is the kinematic similitude. So here actually, so most of the fluid flow phenomena is varying with respect to time. So here this is the kinematic similitude is the similarity of time. So it is the similarity between the velocity parameters of model or the discharge or the acceleration. So various parameters which are relevant to with respect to or which are varying with respect to time. So with respect to the model or with respect to and the prototype or the real field problem, how we can have the similarity or similitude. So this kinematic similitude gives this. So this is the kinematic similitude is the similarity of time. So the last one is the dynamic similitude. So here this dynamic similitude is the similarity between the forces in addition to the geometric similarity and kinematic similarity. So the geometric similitude is the fundamental similarity which we consider. So when we deal with the kinematic similitude, so we have to also we have to consider the geometric similitude. So kinematic similitude is in addition to the geometric similitude, and the third one is the dynamic similitude. So where we have to consider the various forces acting with respect to the prototype or with respect to the real field problem and then model, which are the various forces acting, and then that similitude we have to consider, and then with respect to the dynamic similitude we have to also deal with the geometric similitude and the kinematic similitude which we have seen. So when a particular model study or particular model with respect to the physical model, when the dynamic similitude is there, then that model will be obviously say it will be similarity of geometric as well as kinematic will be already met while the dynamic similitude is obtained. So these three, so while doing the physical modeling, these three important similitude, geometric similitude, kinematic similitude and dynamic similitude is we consider as far as the physical modeling is considered. So now we will go into some more detailed aspect of this various similitude. So first one is the geometric similitude. So here you can see that what we are dealing is two geometrically similar objects must be similar in shape. So here, say for example, when we deal with say the flow over a cylinder, you can see that here the real field problem will be, say the diameter will be very large and a cylinder of this large size is considered, and then when we do the modeling we will consider a small cylinder like this. So say for example this can be 5-meter diameter, and here say if you consider a 1:10 scale, so here it can be 50 centimeter diameter. So here you can see that the shape, the physical modeling which we are doing, so with respect to this flow over a cylinder, so here this is the fluid flow is coming here, so this is the real case and this is the model, and here the real problem. So when we do the scaling, so we have to see that the two geometrically similar objects must be similar in shape. So that is what this geometric similitude gives. So with respect to this, generally we can see that the ratio of various length parameters as like the length of model, the ratio of length of model to length of prototype. So Lm by Lp, that is the length ratio Lr, or the area of the model to area of prototype. So you can see that area is described as square of length. So the model length square divided by prototype length square, so Lr square. Similarly, the volume is considered, the volume of model divided by volume of prototype, Lm cube and divided by Lp cube. So we get the cube of the length ratio. So as far as geometric similitude is concerned, it can be either the length ratio, as far as length is considered, length can be either the length, geometric length or width or the depth, and then area is concerned, we will be having a scale ratio of Lr square, and volume is considered, we will be having scale ratio of with respect to Lr cube. So this is as far as geometric similitude is concerned. So now the kinematic similitude, as we have seen the time scale is important in the when we consider time scale, there the kinematic similitude is considered. So when at geometrically similar points on model and prototype, various parameters which deals with the time like velocity, discharge and accelerations are in a constant ratio. So here we can see that the velocity of the model divided by velocity of prototype. So Vm by Vp is the ratio is Vr, and a time ratio, when we consider time is also Lr by Vr, so that we get so the dimension of V is say meter per second and L is meter. So this comes as time. So time ratio is generally represented as Lr by Vr, and then the acceleration ratio is, so when we consider here Vr square by Lr, that is equal to say here say Lr by T square Tr square, so that meter per second square is coming. So various parameters like time, acceleration, this velocity, and then you can see the discharge. Discharge is concerned, discharge ratio is Qm by Qp, that is the with respect to the discharge of the model divided by the discharge of the prototype, that is the ratio Qr, that is equal to Lrq by Tr. Lr is the length ratio and Tr is the time ratio. So Lrq by Tr. So now when we deal with the kinematic similitude, so you can see that the paths of moving particles are geometrically similar. So you can see hence the streamline patterns are the same. So you can see here the prototype and its model. So here you can see the streamlines. So the streamlines patterns should be also same. And finally the dynamic similarity is concerned. So we have already seen the various forces like the real problem is concerned, various forces acting, the inertia forces, friction forces or viscous forces or gravity forces, pressure forces, elastic forces and surface tension forces. So with respect to this, we will be doing the modeling, the physical modeling. So the dynamic similarity, we have to keep this. So in this case, in addition to the geometric and kinematic similarity, the similarity between the forces acting on the system exists. So inertia force of the model divided by viscous force of the model should be equal to inertia forces of the prototype divided by the viscous force of the prototype. So that gives a constant. Similarly, when we consider the fruit model, so inertia forces of the model divided by gravity force of the model should be equal to inertia force of the prototype divided by the gravity force of the prototype. So that is constant. So here F stands for the force. So finally, when we do the similitude, so we can have the geometric similitude. The similarity parameters are mainly the length ratios, and the kinematic similitude is concerned, the similarity parameters are the discharge ratio, velocity ratio and acceleration ratio. And when we deal with the dynamic similitude, the parameters are force ratio or stress ratio or pressure ratio. And internal constitution, like what we deal with the fluid, the physical modeling and the prototype is concerned, we have to deal with the internal constitution like the and boundary conditions like density and various viscous coefficients, viscosity coefficients like either coefficient dynamic viscosity or kinematic viscosity. So further we will be discussing about the various model laws and model scales with respect to this, the similarity principles and the dimensionless numbers in the next lecture.